Hello class, welcome back from spring break. Here we are continuing on Unit 3. This is our first lesson since we've gone over Newton's 3 laws. Just a quick recap, the first law we got inertia, and the second law we have our unequal forces, force is equal to mass times acceleration, and third law we have our opposite reaction. For every action, there's an equal and opposite reaction. And this lesson is still based on those, so we do need to keep those in mind as we're going through it. But we're going to get into some new kind of vocabulary things that will kind of change the way you think about weight, I'm pretty sure. All right, so lesson 5 is all about gravitational and normal forces. So we've got two new kind of types of forces that we can deal with, that we can add to our free body diagrams, and a whole bunch of questions that can arise from these concepts. So weight, contrary to what society kind of uses it for these days, where we would find our weight using a bathroom scale, right, and we'd record that in kilograms or pounds, right? The truth is, if you're giving a value in kilograms or in pounds, that's actually the mass of the object, right? So weight is coming from the mass and the acceleration due to gravity. So weight is actually a force in our physics world. So when somebody says that they weigh 150 pounds, what they're really saying is that their mass on Earth, right, or their mass is 150 pounds, and they would weigh 150 times 9.81 newtons, right? So this is going to be a little bit tricky starting out because we're so used to thinking about mass and weight being the same thing with the same units, but we're here today to kind of break that notion and come up with this more physically or physics accurate way to think about it, right? So weight will always be a force due to gravity, or a gravitational force, and it will be the mass and the acceleration, right? So mass in kilograms of the object, which is related to how big, how many atoms, right? How dense those atoms are. So mass in kilograms, and g is our acceleration due to gravity. So this here, gravitational field strength, is kind of a new idea. Don't get too hung up on it yet. We're going to go over this a lot more in Unit 5. But another way to think about it is the acceleration due to gravity. So fields are one of the more difficult concepts for students in high school to grasp. So don't spend too long wrestling with that for now. We'll have lots of time to do that later. So our weight is now measured in newtons per kilogram, or in, that's the acceleration, newtons per kilogram or meters per second squared. If you break up a newton into its most basic or most standard units, right, you would see that those actually are the same thing. And, right, multiplying kilograms by newtons per kilogram, we get newtons, or a newton is equal to a kilogram times a meter per second squared, mass times acceleration. All right, so we've talked briefly about the difference between mass and weight. Mass is the amount of matter in an object, while weight is a gravitational force. So try your best to keep those separate in your mind, right? Maybe snicker next time somebody says that they weigh something in kilograms or in pounds, and try your best not to be a smart aleck about it and correct them, but we know now because we took Physics 20. So if a 5 kilogram object is placed, right, this mass will be the same, but on different planets it's going to have different weights. We're all kind of aware of this idea already, right? Different planets will have different gravity. So if we're standing on the moon, we're going to weigh less. So this concept isn't totally new, right? We've been aware of it since we were little kids, but now it's just adding in the proper vocabulary and making more sense of it, right? So mass can be the same. That just means that we have the same amount of matter the same amount of atoms making us up, but the different gravitational pull or gravitational acceleration, depending on what planet we're on, will lead to a different weight. All right, let's try this first example together. So we have a 3.5 gram mass. So they give us the mass right there. And we know we're pulling it upward with a force of 8.7 newtons. And it will be moving at a constant 6 meters per second. Right? So we have a big keyword here, our 6 meters per second, right? Which is constant. So we know that we're dealing with Newton's first law. So this is for our example 1. So Newton's first law, acceleration is equal to 0. And that's because we have constant motion, or a constant speed. Uniform motion is another word we'll use for that. So we're using Newton's first law. We know that all of the forces acting on it have to equal 0, right? We have no acceleration, so we can't have a net external force acting on this 300 gram little mass. Okay, so I'm going to draw out my free body diagram of this. I'll convert it to kilograms because those are our standard units. So we have 0.35 kilogram object. We know that there is a force acting upward on it. So it's pulled up with this force of 8.7 newtons. We know that it's traveling at a constant speed upwards, right? Our acceleration is 0. Our speed is given as 6 meters per second. That part's a bit of a distractor, not going to change your answer. When we're working with dynamics and forces, we're more concerned about acceleration, right? Because force is equal to mass times acceleration. All right, so if it's being pulled up with 8.7 newtons, we need to figure out what the force of air resistance, or better yet, we'll call it AR, air resistance, is in order to keep this object from accelerating. So we know that the net force acting on this object is 0, right? So we're going to have to use our reference system. Up is positive, down is negative. So our net force can be broken up into the force of the pull and the force of air resistance. So we have, I'll just call it F, and we have going down, so it's negative, the force of the air resistance. So simple enough equation. We know that the force of the air resistance, we'd have to add to both sides, right? And we're left with F is equal to positive FAR, which gives us 8.7 newtons as our air resistance, right? And since we made it negative, right, that meant it was down. So the force of air resistance is equal to 8.7 newtons down. So here, drawing becomes really important for the sign convention, right? So by me making this a negative force, right, I'm saying that it's going down, right? And that will carry through each step of the calculation, right? So even though the force of air resistance came out as positive, right, I made it negative right off the bat in my starting equation, so I know that it has to be down. All right, there's our first example. Hopefully that one's making sense and getting us into this idea that, right, force due to gravity is different than mass. The next example should do an even better job of that. All right, now on to our second force of the day, normal force. So gravitational force is also known as weight. normal force is also known as the apparent weight. So this is a really important concept. It's going to come up constantly for the rest of this unit and even on into other units. So try your best to get some good practice in with this and really focus in on the vocabulary here. So in math, we call something normal when it's perpendicular, right? So that's where this name of a normal force comes from. It's always going to be perpendicular to the surface, right? What it really is the force that is the result of pushing two surfaces together. Whether that surface is my hand and this paper, right? Or my hands against each other, we're having forces between both surfaces, right? And as soon as we have two surfaces in contact, we're going to have something known as normal force. So what it really is a reaction force from the surface, either that you're standing on or that you're being pushed up against, right? So as I'm standing on the ground, right, gravity will pull me down, but I'm obviously not accelerating downwards, and that's because the ground or the surface that I'm standing on is pushing back up on me, right? So when an object pushes on a surface, it'll exert an equal and opposite reaction. So that comes from Newton's third law. So I'm pushing down on the earth with a force that's equal to my weight, right, or my gravitational force, and the ground will be pushing back up against me with equal but opposite force, right, because I'm not accelerating in this vertical direction. Right, so just like we can call weight gravitational force, right, we can also call normal force our apparent weight. So you're going to have a lot of problems that are talking about an apparent weight or how heavy you feel, right? That all comes down to this idea of normal force. So think about our weigh scale, right? Our bathroom scale that we use. If you're standing in an elevator, right, and it's traveling at a constant speed, right, you would feel, right, or your apparent weight would be the same as if you weren't moving at all, because you're not accelerating. Now, if you're in an elevator that's accelerating upwards, things start to change, right? So this is like you're on a super fast elevator, it's accelerating you upwards. How do you think that your apparent weight would change, right? The elevator is actually pushing up against you, right, with a greater force than gravity is able to push back down on you, right? So the floor is coming up, accelerating towards you. You're actually going to feel kind of like crumpled together, right? You're going to feel a lot heavier. So that scale will read something larger than if you were traveling at a constant speed or if you were accelerating downwards, right? Because as soon as we start accelerating downwards, now the floor is being dropped out from under us, right? There's less force on this scale in the elevator, right? The force of gravity pulling down on us is in the same direction that we're accelerating. So you're actually going to subtract those accelerations from each other to find the change in that acceleration. So if you're on an elevator that's accelerating down really fast, right, you're going to kind of get that weightless feeling, right? So if you were standing on a scale, it would actually show that same thing, that you're going to have a lower or a smaller apparent weight as the elevator is accelerating down, right? And that's why you kind of get that butterfly in your stomach feeling. I don't know if you've been on the Space Shot or the Tower of Terror, but that's a good kind of real world example of this concept of apparent weight, right? So if you're accelerating up, it feels like your spine's being compressed together, right? You're being shoved down to the ground really hard, so you feel heavier, you have a greater apparent weight. And if you're going down, you have that weightless feeling, those butterflies in your stomach, and the scale will read something lower. You'll have a lower apparent weight, right? And this fourth example, or part of this activity, we're traveling down at the same acceleration due to gravity. So we're in free fall. We have zero apparent weight, no normal force, because gravity is trying to accelerate us down at the same speed that the elevator is moving, right? So we would be in free fall in this case. All right, so normal force always forces between two surfaces. It always has to be perpendicular to the surface. So flat ground, it's going perpendicular or normal to that surface, right? Forming 90-degree angles between the surface always. So whenever you're drawing in a normal force, you're going to have to remember that we're working perpendicular, right? So if it's on a diagonal, right, if this guy's got some skis, he's treading slopes down this mountain, right, that's going to then have to have a different angle for the normal force, so that the normal force is still perpendicular to the surface that this skier is situated on. All right, let's try our last example for lesson 5. We have a 700 Newton person. So they're not giving us their mass here, they're giving us their weight. And that would be their regular weight just on Earth, because it's not really telling us anything different. This person is on an elevator or in an elevator that's accelerating downward at 5.8 meters per second squared. We want to determine their apparent weight. So this question is asking it just in a different way for that weigh scale reading. Okay, so I'm going to just start by drawing in my person with their scale. And they're in an elevator that is accelerating downwards. Right, so the acceleration is down at 5.8 meters per second. Meter per second squared, sorry. So we know how much this person weighs normally, right? The question gives us that they are 700 Newton. So that would be their actual weight, or their gravitational force. Force of gravity acting on this person, as long as they're on Earth, will be 700 Newtons, pointed down towards the center of the Earth. All right, so we know the overall acceleration of this person, the scale, the elevator, right? That's kind of the system we're working with, and it's accelerating downward. We want to determine this force that the scale is reading, right? So we would call that a normal force, right? So the arrows kind of situated weird. You could also have drawn them in, right? The normal force would be the force up on the scale. That makes more logical sense to me, so you can change that to be situated that way in the diagram instead, and then you just have your force of gravity acting down on the person as well. Okay, however you draw it, we still have normal force perpendicular to the surface they're standing on, right, pointed up, and the force of gravity straight down towards the center of the Earth. All right, we want to determine the reading on this scale. So there's a couple steps to this problem. We know the person's weight on Earth, but we don't know their mass in kilograms, right? And if we're trying to find this normal force, we're going to need to use that mass, right, to find force from mass times acceleration. All right, so I'm going to start this question by finding the mass of the person on the elevator, right? So their mass is equal to force divided by acceleration. And in this case, the, sorry, that wouldn't be net force. That's going to be the force of gravity, right? Because they weigh 700 newtons on Earth, right? Not mixing it up with a different planet or with a different total acceleration, net acceleration, right? So on Earth, they weigh 700 newtons, and the gravitational acceleration acceleration due to gravity is 9.81. Sorry, newtons per kilogram. Or just keep it as meters per second squared. So we know from this that the person actually weighs 71.36 kilograms. Right? So person's there standing on the scale. Right? If we didn't have any acceleration of the elevator itself, only acceleration due to gravity, right? We would weigh 700 newtons and have a mass of 71.36. And that mass will be the same mass as when they're accelerating this elevator. All right, so we know we have an acceleration, so we can't use Newton's first law to solve, right? But we're trying to find the unequal forces that give us 5.8 meters per second squared. So here we're going to use Newton's second law. Unequal forces. So our net force is equal to mass times acceleration. We know the mass, we solve for that. We know the acceleration, right? We're going to have to break our net force into its two components. So we had a positive Fn, right? We're saying up is positive, down is negative. And we have a negative Fg. So trying to solve for the apparent weight of this person or that reading on the scale. So we know normal force would be equal to, we'd have to add Fg to both sides. So we have our mass and our acceleration plus the force of gravity, which makes sense, right? Sorry, yes, it does make sense because we have a negative acceleration. Okay, so let's throw in our values. We have a mass of 71.36. I ran out of room. 71.36 kilograms and an acceleration of negative 5.8 meters per second squared. Right, so this sign is really important. And it's important to do kind of logical checks like that as well. If we're accelerating down in an elevator, we should be weighing, or we should have an apparent weight that is less than what we would weigh if we were just at a constant acceleration. Right, so it needs to be subtraction here. And our force of gravity was 700 newtons. All right, throw that in our calculator, 700 minus the product of 71 times 5.8, we get 286 newtons. Right, so Fn, or our scale reading, another way to say it would be the apparent weight, is equal to 286 newtons. And that number is smaller than our 700 newtons if we weren't in an elevator accelerating downwards, which makes sense because as I'm dropping in an elevator, I get that weightless sense to myself, right? Those butterflies in my stomach. So hopefully this lesson went well for you. If it didn't, please email me, let me know, and we will try to clear it up so that the practice problems and homework questions can work out nice and smooth for this one. All right, see you guys for lesson 6.